Hello to the presentation of the paper that we had on IPEC 2024. To introduce Eulerian strong component arc deletion, I would first like to reiterate feedback arc set in a little bit convoluted way. In this problem we are given directed graph and an integer, and we want to remove some small number of edges so that the result has every strongly connected component of size 1. You can notice that removing these blue edges results in a graph that is a directed acyclic graph. In a very similar way, Eulerian strong component arc deletion removes some number of edges, and the aim is that every strongly connected component of the resulting graph is Eulerian. What this means is that we can run an algorithm to find strongly connected components on the result, and this creates some number of strongly connected components, which are black in this picture, and we want these to be balanced, meaning that every vertex has the same number of edges that are coming in and going outside of it, and these edges are within the strongly connected component. All the edges that are such we call active, and all edges that go between strongly connected components, so they cannot return back, we call inactive, and they do not count towards the final balance of a vertex. To go through a few examples, if you have an input that's Eulerian already, you don't need to remove any edges to make it Eulerian, so an empty solution would be a solution. On the other hand, if you need to remove some edges, maybe you can remove them in a way that the graph remains strongly connected. It will become balanced, but it didn't disconnect any components. So in this case, we would have solution of size 2. But in more general case, what could happen is that you remove few edges, and those disconnect the graph into several strongly connected components, and then in each component you could try to find the edges that make it balanced. So we basically have two different types of edges in this case, EF that disconnect them and GH that make them balanced. This problem was asked before, so in 2022 an NP hardness of the vertex deletion variant of this problem was established, and the problem itself was already asked like 12 years ago in this paper, where they studied the variant which needs to have the connected result. So both of these papers mention our problem. To establish NP hardness, remind you reduction of carp to show NP hardness of feedback arc set. In this one we reduce from vertex cover, which is this left instance, and for each vertex we split it in two. We create a single arc between those vertices, and for each edge we create this pair of back arcs between the vertices. The point is that for every edge here on the input we have a 4 cycle on the output, and because you need to cut every cycle, you can cut the 4 cycle anywhere, but you notice that whenever you cut something, you can move it to be the arc that represents the vertex instead of the cross arc. So this backs directly back to the vertex cover. For our problem, we just need to duplicate all these cross edges. And the main observation is that whenever you would have a cycle remaining in the graph, you must have removed one of these edges that are duplicated. So instead of removing that, you can again move it to an edge that represents the vertex, cutting the cycle entirely. Because the vertex cover is NP hard for maximum degree 3, our problem will be NP hard for maximum degree 7. This is this maximum degree result. So this was para NP hardness for maximum degree, and I will show you these other results. Starting with the solution size. To establish that hardness, we need few observations. First is that if we connect two vertices with many edges forward and many edges back, the many meaning more than the budget, then these two vertices must remain in the same strongly connected component in the solution. Second is that if we have a long path that has the middle vertices balanced, then we cannot make it thinner by cutting one edge from each, because again it's longer than the budget. So the only way we can deal with it is to either leave it alone or cut it somewhere. This yields two different gadgets. One is an imbalance gadget that has very well connected vertices in a path and few edges across. These edges basically model edges from A to B that are undeletable. In a second gadget, which is just the path from the previous slide, we can do only two things. We can either cut it or not to cut it, and the optimal solution will do one of these two things. These two gadgets in conjunction allow us to make a choice gadget. If you have undeletable edges here on the left, then to make this middle vertex balanced, you need to cut one of these pairs, which makes one of three choices. You can then propagate this choice further, because whatever you choose may become imbalanced. So to make it balanced, you need to remove some further arcs. And this is how we model choice inside a color class while doing a reduction from multicolored clique. So for each color class, you have this choice gadget. On the right side here, you have different vertices of the same color. And by cutting the path to it, you choose that vertex. From that vertex, then, you propagate these choices to choose the edges. And how this all culminates is that this multicolored clique on the left, between vertices U and V and W, is modeled by cutting those respective paths. And from those, then, cut the edges that go to vertices that model edges between the two color vertices. So this vertex models this UV edge, and because we cut both of its in edges, we disconnected it from the strongly connected component, so the out edges from it become imbalanced and they don't count towards the total balance of S. The point here is that we may cut it in two different ways here, but both of these ways make 4 edges inactive. The other way to make these middle vertices balanced would be to cut one in edge and one out edge, but this would be spending 2 budget to make 2 edges inactive, and because the budget will be set tight, we cannot afford to spend 2 budget to make 2 edges inactive. We need to make 4 edges inactive instead. So this is W1 hardness by a reduction from multicolored clique for the solution size. The slice-wise polynomial algorithm is quite clear because you can just try every possibility. So let me now show the W1 hardness from vertex cover, or for vertex cover. That is done by a reduction from unary bin packing. So in this problem we have items that are encoded in unary, and we have some number of bags of some bounded size. The aim is to fit the items into the bags so that the sums of weights of these items are at most the budget or the size of the bags. This was shown to be W1 hard by the number of bins, or bags as I call them. And how we do this is that we model each bin by its own small imbalance gadget. I will show that one later. And we connect them in total order like this, many copies of the edges. The point of these upper edges is to make it impossible to leave 2 of these bin gadgets in one strongly connected component in the end. Because if we did that, then the imbalance made by these edges would be too high, and it couldn't be balanced in any way. By doing that and connecting each vertex that represents items in this way, we make sure that we basically need to remove that vertex from all but one strongly connected components of the bins. So if we want to assign item U to a bag X, then we don't cut it from it, and we cut it from all the other bins in this manner, which makes you part of the strongly connected component of X. When U remains in the strongly connected component, it creates a cycle which makes this imbalanced gadget more balanced. And if we had item of weight 4, there would be 4 copies of these edges, so it would satisfy 4 edges inside this imbalanced gadget. And because we reduce from a variant where we need to fill in every bag exactly, we will have that the result is balanced. So that's W1 hardness for the vertex cover. The only thing now remaining is the tree width and its FPT variant. So for tree width, the main difficulty is keeping the state in the bag. And what we need to keep is, for every pair of vertices, their reachability. So this can be in 4 different states. Either we cannot reach from one vertex to the other, or maybe it was realized in the past, or it is realized now within the bag, or it will be realized in the future. It's like promised to be there. This makes the state of size 4 to the k squared. Then also we need to keep vertex imbalance for each vertex, which means we count its in degree and out degree within the strongly connected component, but only when in the past graph. But because we know all the reachabilities, also the future reachabilities, we already know all the edges that need to be counted towards this imbalance. And this trivially gives you XP algorithm because these imbalances occupy n to the k space. This already, because we count the balances, gives you FPT for maximum degree and tree width, because the imbalance of a vertex is upper bound by its degree. In very similar manner, we want to do it with solution, but it's not that easy because imbalance with respect to solution can be huge. But the observation is that it's not that different from that one in the input graph. So look at the solution. In the solution, 2 vertices that end up in the same strongly connected component are connected by some number of paths from one to the other and back. Because the graph is Eulerian, there is some flow from one to the other, because these are edge disjoint paths. So let's say the flow here is 2. And maybe the flow could be bigger, but it was cut by the solution. Well, when you now look at the input graph, the maximum flow from U to V cannot be more than k bigger than 1 on the solution. Because every edge of the solution may cut only one path, but at most one path. So they cannot differ that much. And because they don't differ that much, and we can compute the one on the input, we know a small window of imbalances for each vertex where the solution must lie. So we don't compute all the possibilities, but only those that are close to the input, which shows FPT for tree and solution size. We have few open problems. One open question is whether one could design FPT approximation for this problem. And the other one is this feedback arc set which lies here, which could be FPT or W1 hard, but we don't know. Thank you for watching.